Hi, I'm Mark. I'm a lecturer in statistical machine learning at Imperial College. In this course, we were going through the mathematical foundations that we need in order to do dimensionality reduction with principal component analysis. Data in real life is often high dimensional. For example, if we want to estimate the price of our house in a year's time, we can use data that helps us to do this. The type of the house, the size, the number of bedrooms and bathrooms, the value of houses in the neighborhood, when they were bought, the distance to the next train station and park, the number of crimes committed in the neighborhood, the economic climate, and so on and so forth. There are many things that influence the house price, and we collect this information in a data set that we can use to estimate the price of our house. Another example is the 640 by 480 pixels color image, which is a data point in a one-dimensional space, where every pixel corresponds to 3 dimensions, one for each color channel, red, green, and blue. Working with high-dimensional data comes with some difficulties. It is hard to analyze, interpretation is difficult, visualization is nearly impossible, and from a practical point of view, storage can be quite expensive. However, high-dimensional data also has some nice properties. For example, high-dimensional data is often overcomplete. That means many dimensions are redundant and can be explained by a combination of other dimensions. For example, if we took a color image with 4 channels, red, green, blue, and a grayscale channel, then the grayscale channel can be explained by a combination of the other 3 channels, and the image could equally be represented by red, green, and blue alone, as we can reconstruct the grayscale channel just using that information. Dimensionality reduction exploits structure and correlation and allows us to work with a more compact representation of the data, ideally without losing information. We can think of dimensionality reduction as a compression technique similar to JPEG or MP3, which are compression algorithms for images and music. Let's take a small binary image of the handwritten digit 8. We're looking at 28 by 28 pixels, each of which can be either black or white. Therefore, this image can be represented as a 784-dimensional vector. However, in this example, the pixels are not randomly black or white, there's structure. They often have the same value as the neighboring pixels. In this dataset, there are many examples of an 8. They differ a little bit, but they look sufficiently similar that we can identify them as 8. We can use dimensionality reduction now to find a lower dimensional representation of all 8s that is easier to work with than a 784-dimensional vector. The lower dimensional representation of a high-dimensional data point is often called a feature or a code. In this course, we will look at a classical algorithm for linear dimensionality reduction, principal component analysis, or PCA. The purpose of this course is to go through the necessary mathematical details to derive PCA. In the first module, we will look at statistical representations of data, for example using means and variances. And we also describe how means and variances change if we linearly transform our dataset. In the second module, we will look at the geometry in vector spaces and define how to compute distances and angles between vectors. In the third module, we'll use these results to project data onto lower dimensional subspaces, and in the fourth module, we'll derive PCA as a way to reduce dimensionality of data using orthogonal projections. When we work with data, we often need to find compact ways to describe some of its properties. It wouldn't be particularly handy or useful to give somebody the entire dataset. Instead, we can use some statistical properties to describe the data. For example, we can say something about the center or the average of the data, or the spread or orientation. In the following videos, we will be looking at exactly these kind of statistical properties and discuss mean values to describe average data points, variances that make statements about the spread, and covariances which characterize orientation and correlations. Data is often compactly described by some of its statistical properties, such as the mean and the variance. In this video, we'll explain how to compute means of datasets. The mean of a dataset describes the average data point. The mean does not have to be a typical data point, and it also does not need to be part of the dataset itself. For example, if we look at a set of images of the digit 8, the average image looks like this. It has properties of all images in the dataset, but it is not part of the dataset itself. We obtain the average 8 as follows. Remember that an image can be represented as a long vector in a high-dimensional vector space by stacking all pixels together. After transforming all images into these vectors, we take all image vectors in our dataset, add them together, and divide by the number of images in the dataset. This gives us the average image vector. If we then reshape that vector into an image again, we get the average digit in the dataset. Here's an example with 4 8s. The mean of the first one is just the image itself, but when we add the second image, we see that the average image now contains properties from both images. When we add the third image, the mean image is all 3 images on top of each other divided by 3. After the fourth image, we can still see characteristics of all 4 images in the average image. When we add more images to our dataset, the average digit becomes a bit more blurry. And if we take all 8s in our dataset, we get this 8 as the average image. Generally, if we have a dataset x1 to xn, let's say D consists of data points x1 to xn, we get the mean value or the expected value of this dataset as follows. We write, well, the expected value of D is 1 over the number of data points, so this is n, times the sum n equals 1 to capital N of xn. So we sum up all data points in our dataset and divide by the number of data points that we have. Let's look at an example. I create a dataset consisting of the 5 numbers that I get when I roll 5 dice. We got 1, 2, 4, 6, and 6. So let's write this down. So we're going to call this D prime is 1, 2, 4, 6, and 6. And now the expected value, or the average, of this data set is the sum of all elements in this data set. So this is 1 plus 2 plus 4 plus 6 plus 6 divided by the number of elements in our data set, and that is 5. So if we sum these things together and divide by 5, we get 19 over 5, or 3.8. We can clearly see that 3.8 is not part of the dataset and cannot even be achieved by rolling a dice. Therefore, it is also worthwhile keeping in mind that although the mean is the average of the dataset, it does not have to be a typical instance. In this video, we computed the mean value of datasets as the average data point. The mean value doesn't have to be part of the dataset. In the next video, we'll introduce variances to describe the spread of the data around the mean value. In the last video, we discussed mean values of datasets which represent an average data point. In this video, we will look at variances to describe other properties of a dataset. Let us have a look at 2 different datasets, D1 and D2. D1 is represented by the blue dots located at 1, 2, 4, and 5, and D2 is represented by the red squares at -1, 3, and 7. D1 and D2 have the same mean, which is 3, but the data points in D2 are less concentrated around the mean than the data points in D1. Remember, the mean value is the data point we would expect on average, but to describe the concentration of data points around the mean value, we can use the concept of the variance. The variance is used to characterize the variability or spread of data points in a dataset. In one dimension, we can look at the average squared distance of a data point from the mean value of this dataset. Okay, let's do this for D1 and D2. So D1 was 1, 2, 4, and 5, and the mean value or expected value of D1 was 3, and D2 was -1, 3, and 7 with exactly the same mean value. So now we want to compute the average squared distance of D1 from the mean and from D2 from the same mean. So let's do this for D1 first. So we get 1 minus 3 squared plus 2 minus 3 squared plus 4 minus 3 squared plus 5 minus 3 squared. So these are the sum of the average of the squared distances, and to get the average we divide by 4, which is the number of data points in D1. So if we do the computation, we get 4 plus 1 plus 1 plus 4 divided by 4, which is 10 over 4. So now we do the same for D2. And for D2 we get minus 1 minus 3 squared plus 3 minus 3 squared plus 7 minus 3 squared. And we divide by the number of data points in D2, which is 3. And we get 16 plus 0 plus 16 divided by 3, which is 32 over 3. So now this number is now bigger than this number, which means that the average squared distance of D2 from the mean value is bigger than the average squared distance of D1 from the mean value, which indicates that the spread of the data is higher in D2 than in D1. So what we have done can be formalized. So assuming we have a data set consisting of n data points x1 to xn, then we can define the average squared distance as the following. So we have x1 up to xn, and then we define this to be our data set x, and we define now the variance of this data set to be 1 over n times the sum of small n equals 1 to big N of xn minus mu squared, where mu is the mean value of the data set x. Yeah, so what we have done here is exactly the same as what we did before with D1 and D2. We computed an average squared distance of the data points in the data set from the mean value of the data set. And now we can also make some statements about this. First, the variance as defined here can never be negative because we just sum up squared values. And that also means we can take the square root of the variance, and this is called the standard deviation. The standard deviation is expressed in the same units as the mean value, whereas the variance, unfortunately, is expressed in squared units, so comparing them is quite difficult. Therefore, when we talk about spread of the data, we usually look at standard deviations. So in this video, we looked at variances of one-dimensional data sets, and in the next video, we will generalize this to higher dimensions. In the last video, we looked at variances for one-dimensional data sets. And in this video, we were looking at variances for high-dimensional data sets. The intuition and definition of the variance we had earlier does not really work in the same way in high dimensions, and squaring vectors is not really defined. Assuming we have a two-dimensional data set, we can now compute variances in the x direction and the y direction. But these variances are insufficient to fully describe what is going on in the data set. In particular, we only have the variation of the data in either direction, independent of the other direction, but we may also be interested in the relationship between the x and y variables. And this is where the concept of the covariance between these components comes into play. Let's have a look at an example in two dimensions. For this data set, we can compute the variances in the y direction and the variances in the x direction, which are indicated by these vertical and horizontal bars. But this can be insufficient, because we can look at other examples where the variances in the x and y directions are the same, but the data set look very different. If we look at this particular example, we have a different shape of the data set, but the variances in the x direction and the variance in the y direction are exactly the same, and the mean values of these data sets are also identical. And I can look at different sets, like this one here and this one. These four data sets look very different, we've seen 4 different examples with 4 different properties or shapes of the data sets, but the variances in x and the variances in y and the mean values are identical. If we exclusively focus on the horizontal and vertical spread of the data, we can't explain any correlation between x and y. In this last figure, we can clearly see that on average, if the x value of a data point increases, then on average, the y value decreases, so that x and y are negatively correlated. This correlation can be captured by extending the notion of the variance to what is called the covariance of the data. The covariance between x and y is defined as follows. So covariance between x and y is defined as the expected value of x minus the mean in the x direction times y minus the mean in the y direction. Just write mu x is the expected value in the x direction and mu y is the expected value of the y coordinates. For the 2D data, we can therefore obtain 4 quantities of interest. We obtain the variance of x, we get the variance of y, and we also have the covariance terms, the covariance between x and y and the covariance between y and x. So we summarize these values in this matrix called the covariance matrix with 4 entries. And in the top left corner, we have the variance in the x direction. Then we get the covariance term between x and y in the top right corner, the covariance between y and x in the bottom left corner, and the variance of y in the bottom right corner. If the covariance between x and y is positive, then on average the y value increases if we increase x, and if the covariance between x and y is negative, then the y value decreases if we increase x on average. If the covariance between x and y is 0, then x and y have nothing to do with each other. They are uncorrelated. The covariance matrix is always a symmetric, positive, definite matrix with the variances on the diagonal and the cross covariances or covariances on the off diagonals. If we now look at d-dimensional data sets, let's say we have a data set consisting of n vectors, x1 to xn, and every xi is in Rd, then we can compute the variance of this data set as 1 over n times the sum I equals 1 to capital N of xi minus mu times xi minus mu transpose, where mu is the mean of the data set, and this is called the covariance matrix of the data, and this is a d by d matrix. So previously we looked at means and variances to describe statistical properties of data sets. In this video we'll discuss what happens to means and variances when we linear transform the data set. That means we shift it around or stretch it. So let's look at a data set D, which is given by these blue dots over here. So we have a data set D, which is -1, 2, and 3. Now let's compute the mean value of this data set to start with. So the expected value of D is -1 plus 2 plus 3 divided by 3, which is 4 over 3. So I'm indicating the mean value of this data set by this blue star. So now the question is, what happens to this data set when we shift it? So let's have a look at a shift by 2 to the right. So we end up with these red dots now. What happens to the mean value of this data set if we shift the data set, the original data set, to the right? Well, the answer is the mean also shifts by 2. So let's define D prime to be the data set 1, 4, and 5, which is D plus 2 for every individual component in D. Then the expected value of D prime is 1 plus 4 plus 5 divided by 3, which is 10 over 3. And in particular, we can write this in a slightly different way. We can write this as 4 over 3, which comes from here, plus 2, which is the shift or the offset of the original data set. So we can generalize this now to general shifts. We can write an expected value of D plus A, where A is a constant factor, is A plus the expected value of D. So up to this point, we know what happens to the mean of the data set when we shift the data set. But what happens if we stretch the data set? Let's say we also stretch by a factor 2, and that means we multiply every individual component in the data set D by 2. So then we end up with this data set on the indicated by the red dots here, and we define D double prime to be -2, 4, and 6. And if we now compute the mean of D double prime, then we end up with -2 plus 4 plus 6 divided by 3, which is 8 over 3. And we can rewrite that again in a convenient way, which is 4 over 3, which again comes from here, times 2, which is the scaling factor. So in general, we can write that the expected value of alpha times D is alpha times the expected value of D. Putting everything together, we can shift and scale our original data set, and the new mean of this linear transformation is given as follows. So if we compute the expected value of alpha times D plus A, we get alpha times the expected value of D plus A, where alpha is the scaling factor and A is the shift. In this video, we looked at the effect of linear transformations on the mean value of a data set. In the next video, we will look at exactly the same for the variances. We've seen what shifting and scaling a data set does to the mean. Now let's have a look at the effects on the variance. Remember that the variance is a measure of the spread of the data. What do we expect when a data set is shifted? Let's have a look at this data set over here. We have 3 data points given at -1, +2, and +3. And now we are shifting the data set towards the right. The variance of the data set is indicated by the blue bar at the bottom. The shifted data set is now given by the red dots, and we shift every individual data point by 2. So the question is now, what happens to the variance? Well, the shift of the data does not really affect the relation of the data points among themselves. Therefore, the variance does not change. The variance is identical. So the variance of the blue data set is identical to the variance of the red data set. Therefore, a general result is that if we have the variance of D, that is exactly the same as the variance of our data set D plus A, where A is an offset applied to every individual element of D. Let's now scale the data set and see what effect that has on the variance of the data. So we're going to take exactly the same data set as before. The variance is indicated by the blue bar. And we're going to scale every individual data point by 2. So the question is, what is the variance of 2 times d? So new data set is indicated by these red dots. Remember that the variance is the average squared distance of the data points from the mean. If we scale the data set by a factor of 2, the distance of every data point to the mean is scaled by 2. But the squared distance is scaled by 4. And the variance is therefore 4 times as big as it used to be. And our next result is that the variance of alpha times d is alpha squared times the variance of d, where alpha is a real number that scales every individual element in the data set d. Now let's have a look at high-dimensional problems. Assume we have a data set d, which is a collection of data points x1 to xn, and the xi live in Rp. Remember, the variance of this data set is given by a covariance matrix. If we perform a linear transformation of every data point, say axi plus b, for a given matrix A and an offset vector b, the question is, what happens to our data set if we do this to every single data point? Well, we get the covariance matrix of the transformed data set as follows. We're getting the variance of A times D plus B is A times the variance of D times A transpose. In this video, we saw what effects a linear transformation of a dataset has on the mean and the variance. In particular, we saw that shifting data has only an effect on the mean, but not the variance, where scaling the data affects both the mean and the variance. It is often necessary to measure similarity between data points. In the context of dimensionality reduction, we are interested in finding compact representations of data that live in a lower dimensional space, but which are similar to the original data. One of the key concepts we will be looking at in this course is orthogonality. We'll use orthogonal projections of data points as a way to compress data while minimizing the loss of information. Thinking of data points as vectors in the vector space will allow us to look at two types of similarity between data points: distances of data points from each other and the angle between these two data points. Let's have a look at an example. Assume we're living in a two-dimensional world and we have two vectors x and y. Things that we will be discussing in this course are how to compute the length of individual vectors. So that means for x, that means the length of this line here. We will be looking at angles between two vectors, and we would be looking at distances between individual data points or vectors in this vector space. So in this case, you would be interested in the distance between x and y. In order to measure angles and compute lengths and distances, we need to equip the vector space with an inner product which allows us to talk about geometric properties in this vector space. In the next videos, we will be looking at computing lengths, distances between vectors, and angles between vectors. In order to measure angles, lengths, and distances, we need to equip the vector space with an inner product which allows us to talk about geometric properties in a vector space. An example of an inner product that we may know already is the dot product between two vectors x and y. If x and y are two vectors in Rn, then the dot product is defined as x transpose y is the sum I equals 1 to n of xi times yi, where x and y are n-dimensional vectors. The length of x is then defined as the square root of the dot product of x with itself. So the length of x is the square root of x transpose x, which we can also write as the square root of the sum of I equals 1 to n of xi squared. Let's have a look at an example. We take a vector x as 1, 2 and a vector y as 2, 1 in a two-dimensional plane. Then we can compute the length of the vector of x as the square root of 1 squared plus 2 squared, which is the square root of 5, and the length of y similarly is the square root of 5 as well. If we're interested in the distance between two vectors x and y, we simply compute the length of the difference vector. So we generally define then the distance between x and y to be the length or the norm of x minus y, which is the square root of x minus y transpose times x minus y. So now let's compute the distance between our two vectors over here. So the distance between these two vectors is effectively just the length of this difference. So we can write this as the norm of 1, 2 minus 2, 1. So this is our difference vector, and that is the norm of minus 1 and 1. And this is the square root of 1 plus 1, which is the square root of 2. So the length of this yellow segment is square root 2. So the last thing we are still interested in is the angle between two vectors, and we can compute the angle also using the dot product. The cosine of the angle, let's call this angle alpha. So the cosine of alpha is given by x transpose y divided by the length of x times the length of y. And in our example over here, we'll get that the cosine of the angle between x and y is x transpose times y, which is 4, divided by the length of x times the length of y. But we've done these computations already, which come from here. So it's square root 5 in any case. So therefore, we get the cosine alpha is 4 over 5, which corresponds to approximately 0.64 radians. And that is our angle alpha between these two vectors. In this video, we looked at dot products as special cases of inner products to compute lengths of vectors, to compute distances between vectors, and angles between two vectors. And in part 2 of this video, we will be looking at general inner products to compute exactly the same quantities. Previously, we looked at the dot product to compute angles, lengths, and distances. In this video, we will be looking at generalizations of the dot product in order to compute angles, lengths, and distances. Sometimes it is necessary to use an unconventional way to measure these geometric properties, and the inner product allows us to do exactly this kind of thing. An inner product is a generalization of the dot product, but with the same idea in mind. We want to express geometric properties such as lengths and angles between vectors. Let's define what an inner product actually is. So let's write the definition. We're looking at two vectors for any vectors x and y in a vector space V. An inner product is defined as a symmetric, positive, definite bilinear mapping. So let's see what that means. We take a mapping that takes two inputs out of this vector space. It's a mapping from V times V to the real numbers. And we say this function is symmetric, positive definite, and bilinear. So let's unpack this a little bit. Let's start with bilinearity. Bilinear means that for vectors x, y, and z in this vector space and real numbers lambda, we get that lambda times x plus z and y, so the scalar, the inner product between lambda x plus z and y can be written as lambda times the inner product between x and y plus the inner product between z and y. So this is linearity only in the first argument of this function, and we require to have linearity also for the second argument of this function. So similarly, we will then require that the inner product between x and lambda y plus z is lambda times the inner product between x and y plus the inner product between x and z. So this means linearity also in the second argument, and that's the reason why this is called bilinear. It means linearity in both arguments of this function. So positive definite means that the inner product of x with itself is greater or equal to 0, and equality holds if and only if x is the 0 vector. And the last component that we need is symmetry, and symmetric means that the inner product of x and y is the same as the inner product of y and x. So the order does not matter. Let's have a look at an example in R2. If we define our inner product to be x transpose times the identity matrix times y, then we get exactly the dot product that we are very familiar with. But now let's have a look at a different example where we define our inner product to be x transpose times A times y, where A is the matrix 2, 1, 1, 2. Then we can also write our inner product to be 2 times x1, y1 plus x2, y1 plus x1, y2 plus 2 times x2, y2, and this inner product is different from the dot product. Any symmetric positive definite matrix in this equation defines a valid inner product. In this video, we introduce the concept of an inner product, which we will use in the next videos to discuss geometric properties of vectors, such as lengths and angles. In the last video, we defined inner products. Now we will use inner products to compute the lengths of vectors and distances between vectors. The length of a vector is defined via the inner product using the following equation. So the length of a vector x is defined as the square root of the inner product of x with itself. Remember that the inner product is positive definite. That means this expression is greater or equal than 0. Therefore, we can take this square root. We can now also see that the length of a vector depends on the inner product, and depending on the choice of the inner product, the length of a vector can be quite different. Similarly, the geometry in the vector space can be very different. The length of x is also called the norm of x. So let's have a look at an example. Assume we're interested in computing the length of a vector in 2 dimensions, and x is given as the vector 1, 1. So in a diagram, we have 1 here and approximately here. Then our vector x would be here, and now we're interested in computing the length of this vector. So in order to compute the length of the vector, we need to define an inner product. So why don't we start with the standard dot product? So if we define xy to be x transpose y, so the inner product of x and y to be x transpose times y, then the length of x is the square root of 2. So it's 1 squared plus 1 squared, and we take the square root of this. Now let's have a look at a different inner product. Let's define xy to be x transpose times 1 minus a half 1 times y, which we can also write as x1 times y1 minus a half x1 y2 plus x2 y1 plus x2 y2. Using the definition of this inner product, then the length of a vector is the square root of x1 squared minus a half x1 x2 plus x2 x1 plus x2 squared. And this is identical to the square root of x1 squared minus x1 x2 plus x2 squared. And we'll get smaller values than the dot product definition up here if this expression is positive. If we now use the definition of this inner product to compute the length of our vector up here, we will get that the squared norm, or the inner product of x with itself, is 1 plus 1 minus 1, which is 1, and therefore the norm of x is just 1. And 1 in this case would be the length of the vector using this unusual definition of an inner product, whereas the same vector would be longer had we used the dot product up here. The norm that we just looked at also has some nice properties. Let me write a few of those down. So in particular, one of the properties is that if we take a vector and stretch it by a scalar lambda, then the norm of this stretched version is the absolute value of lambda times the norm of x. The second property is the triangle inequality. Which says that the norm of x plus y is smaller or equal to than the norm of x plus the norm of y. Let's have a look at an illustration. So let's assume we have our coordinate system in 2 dimensions, and we use the standard vectors x equals 1, 0. So x would be sitting exactly here. So this is x, and y is 0, 1. Then x plus y is sitting here. If we use the dot product as our inner product, then the norm of x is 1, which is the same as the norm of y. And the norm of x plus y is square root 2. So what the triangle inequality says that x plus y norm is smaller or equal than the norm of x plus the norm of y. And that is also true in our case because square root of 2 is smaller or equal than 2. And there's another inequality I would like to mention, which is the Cauchy-Schwarz inequality. And that one says that the absolute value of the inner product of x with y is smaller or equal than the product of the individual norms of the two vectors. In this video, we looked at lengths of vectors using the definition of inner products. And now we're going to use this to compute distances between vectors in the next video. Now that we know how to compute the length of a vector, we can also compute distances between any two vectors x and y. The distance between two vectors is defined as the length of the difference vector. So we can write the distance between x and y to be the norm of x minus y. And as we know, this depends on the definition of our inner product. If we use a dot product, then the distance is called the Euclidean distance. Let's have a look at an example. We're going to look at two vectors, x and y. We're going to say x is 2, 3, and y is 4, 1. So let's draw this. So this is x, and y is over here. In order to compute the distance between these two vectors, the first thing we actually need to do is let's have a look at this difference vector. So x minus y is 2 minus 4 in the first component and 3 minus 1 in the second component. That means we get minus 2 and plus 2 as the difference vector. So now we can define inner products. And let's now use the dot product as our first example. If we use the dot product to compute the length of this difference vector, we will get the square root of the first component squared plus the second component squared, which is 4 plus 4, and that's the square root of 8. And if we use a different inner product, let's say we define the inner product between x and y to be x transpose times 1 minus half minus a half and 1 times y, then if we now use the difference vector here, the result will be the square root of 12. So we can see that depending on the choice of our inner product, we will get different answers of what the distance between x and y actually is. In this video, we computed distances between two vectors using inner products. And we saw that depending on the inner product, the distance between these two vectors can differ. Previously, we have looked at lengths of vectors and distances between vectors. In this video, we'll introduce angles as a second important geometric concept that will allow us to define orthogonality. Orthogonality is central to projections and dimensionality reduction. Similar to lengths and distances, the angle between two vectors is defined through the inner product. If we have two vectors, x and y, and we want to determine the angle between them, we can use the following relationship. the cosine of this angle between the two vectors is given by the inner product between the two vectors divided by the norm of x times the norm of y. Let us have a look at an example. And let's compute an angle between two vectors x, which is 1, 1, and y, which is 1, 2. And let's quickly draw this. This is x. And this is y. And we're interested in the angle omega between those. If we use a dot product as the inner product, we get that the cosine of omega is x transpose y divided by the square root of x transpose x times y transpose y, which is 3 divided by the square root of 10. This means the angle is approximately 0.32 radians or 18 degrees. Intuitively, the angle between two vectors tells us how similar their orientations are. Let's look at another example in 2D, again with the dot product as the inner product. We're going to look at the same vector x that we used to have before, so x equals 1, 1, which is this vector over here. And now we choose y to be -1 and +1, and this is this vector. Now we're going to compute the angle between these two vectors, and we see that the cosine of this angle between x and y is, with the dot product, x transpose times y divided by the norm of x times the norm of y. And this evaluates to 0. This means that omega is pi over 2 in radians, or if we want to say this in degrees, we have 90 degrees. This is an example where two vectors are orthogonal. Generally, the inner product allows us to characterize orthogonality. Two vectors x and y, where x and y are non-zero vectors, are orthogonal if and only if their inner product is 0. This also means that orthogonality is defined with respect to an inner product, and vectors that are orthogonal with respect to one inner product do not have to be orthogonal with respect to another inner product. Let's take these two vectors that we just had, where the dot product between them gave that they are orthogonal, but now we're going to choose a different inner product. In particular, we're going to choose the inner product between x and y to be x transpose times the matrix 2, 0, 0, 1 times y. And if we choose this inner product, it follows that the inner product between x and y is -1. This means that the two vectors are not orthogonal with respect to this particular inner product. From a geometric point of view, we can think of two orthogonal vectors as two vectors that are most dissimilar and have nothing in common besides the origin. We can also find a basis of a vector space such that the basis vectors are all orthogonal to each other. That means we get the inner product between bi and bj is 0 if I is not the same index as j. And we can also use the inner product to normalize these basis vectors. That means we can make sure that every bi has length 1. Then we call this an orthonormal basis. In this video, we discussed how to compute angles between vectors using inner products. We also introduced the concept of orthogonality and saw that vectors may be orthogonal with respect to one inner product, but not necessarily if we change the inner product. We will be exploiting orthogonality later on in the course. If we have a vector and we want to compute the smallest difference vector to any point on a line that does not contain the vector, then we will end up finding a point on the line such that the segment between the point and the original vector is orthogonal to that line. In the previous videos, we looked at properties of inner products to compute lengths, angles, and distances. We focused on inner products of finite-dimensional vector spaces. In this video, we will look at two examples of inner products of other types of vectors: inner products of functions and inner products of random variables. The inner products we discussed so far were defined for vectors with a finite number of entries, and we can think of these vectors as discrete functions with a finite number of function values. The concept of an inner product can be generalized to continuous valued functions as well. And then the sum over individual components of vectors turns into an integral. Then the inner product between two functions is defined as follows. We can write that the inner product between two functions u and v is the integral over an interval from a to b of u of x times v of x dx. And as with our normal inner product, we can define norms and orthogonality by looking at this inner product. If that integral evaluates to 0, the functions u and v are orthogonal. Let's have a look at an example. If we choose u of x equals sine x and v of x is cosine of x, and we define f of x to be u of x times v of x, which is sine x times cosine x, then we're going to end up with this function. This function is sine x times cosine x. We see that this function is odd, which means that f of minus x equals minus f of x. If we choose the integral limit to be minus pi and plus pi, then the integral of this product sine of x times cosine of x evaluates to 0. And that means that sine and cosine are orthogonal. And it actually holds that if we look at a set of functions, say 1 cosine x, cosine of 2x, cosine 3x, and so on, that all of these functions are orthogonal to each other if we integrate from minus pi to plus pi. Another example for defining an inner product between unusual types are random variables or random vectors. If we have two random variables which are uncorrelated, then we know the following relationship. We know that the variance of x plus y is the variance of x plus the variance of y, where x and y are random variables. If you remember that variances are measured in squared units, this looks very much like the Pythagorean theorem for right triangles. That one states that c squared equals a squared plus b squared. If we look at triangles of this form, where this is a, b, and this is c. Let's see whether we can find a geometric interpretation of the variance relation of uncorrelated random variables. Random variables can be considered vectors in a vector space, and we can define inner products to obtain geometric properties of these random variables. If we define the inner product between two random variables, so between x and y, to be the covariance between x and y, we see that the covariance is symmetric, positive definite, and linear. So linearity would mean that the covariance of lambda times x plus y and z, where x, y, and z are random variables, and lambda is a real number, is lambda times the covariance between x and z plus the covariance between y and z. And if the length of a random variable is the square root of the covariance between of x with itself, which is the square root of the variance of x, then this is the standard deviation of the random variable x. So this is the length of a random variable. Therefore, the zero vector is a vector that has no uncertainty. That means standard deviation is 0. If we now look at the angle between two random variables, we get the following relationship. We get the cosine of theta, which is the angle between two random variables, is by definition the inner product between the two random variables divided by the length of the first random variable times the length of the second random variable. And if we now write this out using the definition of our inner product, we get the covariance between x and y divided by the square root of the variance of x times the variance of y. And this evaluates to 0 if and only if the covariance between x and y is 0, and that is the case when x and y are uncorrelated. Coming back now to our geometric interpretation, we would now replace a with the standard deviation of x, b is the standard deviation of y, and c is the square root of the variance of x plus the variance of y. And this is how we get our geometric interpretation of random variables. In this video, we looked at inner products of rather unusual objects, functions and random variables. However, even with functions and random variables, the inner product allows us to think about lengths and angles between these objects. In the case of random variables, we saw that the variance of the sum of two uncorrelated random variables can be geometrically interpreted using the Pythagorean theorem. High-dimensional data is often hard to analyze or visualize. However, high-dimensional data quite often possesses the property that only a few dimensions contain most information, and most other dimensions are not essential to describe key properties of the data. When we compress or visualize high-dimensional data, we lose information. Ideally, we find the most informative dimensions in the data and keep them when we compress the data and ignore the irrelevant dimensions. In this course, we will have a close look at orthogonal projections, which play a central role in algorithms for dimensionality reduction. In this video, we'll look at orthogonal projections of vectors onto one-dimensional subspaces. Let's look at an illustration. We're given vector x in 2 dimensions, and x can be represented as a linear combination of the basis vectors of R2. We also have a one-dimensional subspace U with a basis vector b. That means all vectors in U can be represented as lambda times b for some lambda. Now we're interested in finding a vector in U that is closest to x. Let's have a look at this. When I compute the length of the difference of all vectors in U and the vector x, I'm getting the graph on the right. It turns out that we can find the vector in U that is closest to x by an orthogonal projection of x onto U. That means the difference vector of x and its projection is orthogonal to U. Overall, we are looking for the orthogonal projection of x onto U, and we will denote this projection by pi u of x. The projection has 2 important properties. First, since pi u of x is in U, it follows that there exists a lambda in R such that pi u of x can be written as lambda times b, a multiple of the basis vector that spans U. Then lambda is the coordinate of the projection with respect to the basis b of the subspace U. The second property is that the difference vector of x and its projection onto U is orthogonal to U. That means it's orthogonal to the basis vector that spans U. So the second property is that the inner product between B and the difference between pi u of x and x is 0. So that's the orthogonality condition. These properties generally hold for any x in Rd and one-dimensional subspaces U. Now let's exploit these two properties to find pi u of x. I've drawn the setting once more over here. We have a two-dimensional vector x. We have a one-dimensional subspace U, which is spanned by the vector B. And we're interested in finding the orthogonal projection of x onto U, which we call pi u of x. And we have two conditions for pi u of x. The first thing is that since pi u of x is an element of U, we can write it as a scaled version of the vector B. So there must be a lambda in R such that pi u of x is lambda times B. And the second condition is the orthogonality condition, that the difference vector between x and pi u of x is orthogonal to U, which means it's orthogonal to the spanning vector B. And now let's exploit these two properties to find pi u of x. So first, we use the condition that B and pi u of x minus x inner product is 0, which is equivalent to that the inner product of B and pi u of x minus the inner product of B and x is 0, where we exploited now the linearity of the inner product. Now we're going to rewrite pi u of x as lambda times B. So this is equivalent to B times lambda B, or inner product with lambda B minus the inner product of B and x. That must be 0. Now we can move the lambda out again because of the linearity of the inner product, which is then lambda times the squared norm of B minus the inner product of B and x must be 0. And that is equivalent to lambda is the inner product of B with x divided by the squared norm of B. So now we found lambda, which is the coordinate of our projection with respect to the basis B. And that means that our projection using the first condition is lambda times B, which is now the inner product of B with x divided by the square norm of B times B. If we choose the dot product as the inner product, we can rewrite this in a slightly different way. So we would get B transpose times x times B divided by the squared norm of B. So now, given that this one is a scalar, we can just move it over here. So this is equivalent then to saying B times B transpose divided by the squared norm of B times x is our projected point. And if we look at this, this is a matrix, and this matrix is a projection matrix that projects any point in 2 dimensions onto the one-dimensional subspace. So now if we look at the special case of B having norm 1, then we get a much simpler result, and we would get, so if the norm of B equals 1, then we will get that lambda is B transpose times x, and pi u of x is B times B transpose times x. So you would get the coordinate of the projected point with respect to the basis B just by looking at the dot product of B with X. And the projection matrix is simply given by B times B transpose. Let me make a comment at the end. Our projection pi u of x is still a vector in Rd. However, we no longer require d coordinates to represent it, but we only need a single one, which is the lambda. In this video, we discussed orthogonal projections of vectors onto one-dimensional subspaces. We arrived at the solution by making two observations. We must be able to represent the projected point using a multiple of the basis vector that spans the subspace, and the difference vector between the original vector and its projection is orthogonal to the subspace. In the next video, we will look at an example. In the last video, we derived the formula for projections of vectors onto a one-dimensional subspace. In particular, we arrived at this equation if we choose the dot product as the inner product. Here, x is a d-dimensional vector, and b is the basis vector that spans that one-dimensional subspace that we want to project x onto. In this video, we're going to look at an example. Assume our vector b that spans our one-dimensional subspace is the vector 2, 1, and the vector x we want to project onto that subspace is given by 1, 2. Let's quickly draw this. So x is the vector 1, 2. So x is living over here. And the vector b is going to be the vector 2, 1. And so this is b. And b spanning our subspace means that our subspace U is going to extend along this line. So now we're interested in computing the orthogonal projection of x onto U. So using now this equation here, we get, so x transpose times b is 2 plus 2. And now we divide by the squared norm of b. So the length of b is 2 squared plus 1 squared square root. So overall, we get the squared norm to be 5. And then times b will get us to 2, 1. So overall, 4 over 5 times the vector 2, 1. This means that our orthogonal projection is 4 over 5 times the vector b. That means if we take 4/5 of this vector, then we will get to our orthogonal projection. So this point here is now pi u of x, so the orthogonal projection of x onto u. And the length of this segment is 4/5 times the length of b. We've gone through orthogonal projections onto one-dimensional subspaces. In the next video, we're going to look at orthogonal projections onto higher-dimensional subspaces. In the last video, we learned about orthogonal projections onto one-dimensional subspaces. In this video, we look at the general case of orthogonal projections onto n-dimensional subspaces. For this, we'll exploit the same concepts that worked in the one-dimensional case. Let's start with an illustration. We're going to look at a case where we have a vector x that is living in a three-dimensional space, and we define a subspace, a two-dimensional subspace U, which has basis vectors b1 and b2, which are, for example, this vector, and b2 is this vector. So we write U is spanned by b1 and b2. So U in this case would be the plane down here. So this is U. So now we're looking at the orthogonal projection of x onto U, and we're going to denote this by pi u of x. So that projection is going to look something like this. That's the projection point. So this is the orthogonal projection of x onto the subspace U. So we can already make two observations. The first thing is that because pi u of x is an element of U, it can be represented as a linear combination of the basis vectors of U. So that means we can write pi u of x is lambda 1 times b1 plus lambda 2 times b2 for appropriate values of lambda 1 and lambda 2. And the second property is that the difference vector of x minus pi u of x, so this vector over here, is orthogonal to U, which means it's orthogonal to all basis vectors of U. And we can now use the inner product for this, and we can write that x minus pi u of x inner product with b1 must be 0, and the same is true for b2. But now let's formulate our intuition for the general case where x is a d-dimensional vector and we're going to look at an m-dimensional subspace U. Okay, let's derive this result. I copied our two insights up here and I have defined two quantities. A lambda vector which consists of all these lambda I here, and a B matrix where we just concatenate all basis vectors of our subspace U. Now, with this definition, we can also write pi u of x equals b times lambda. Let's assume we use the dot product as our inner product. Now, if we use our second property, we'll get that so pi u of x minus x inner product with bi is now equivalently written as the inner product of b lambda minus x and bi, and this needs to be 0, where I just used the definition of p u of x in here. So now we can simplify this by exploiting the linearity of the inner product, and we'll get b lambda times, or inner product with bi minus the inner product of x with bi needs to be 0. And this holds for I equals 1 to m. With the inner product, we can now write this in the following way. We can write this as lambda transpose times b transpose times bi minus x transpose times bi equals 0 for I equals 1 to m. And now we can write this as a set of conditions, and if we summarize this, we would get lambda transpose times b transpose times b minus x transpose times b must be 0. Now we need to talk here about an m-dimensional 0 vector. What we would like to do now is we would like to identify lambda. For this, we are going to right multiply the inverse of b transpose times b onto the entire equation. And then we get lambda transpose equals x transpose times b times b transpose b inverse, which then also means we can write lambda as the transpose of this entire expression. We get B transpose B inverse. So this matrix is symmetric, so its transpose is the same as the original matrix, times B transpose X. So now we have identified lambda to be this, but we also know that our projection point can be written as B times lambda. So this means we will get pi u of x as B times lambda, which is B times B transpose B inverse times B transpose X. We can now identify this expression as the projection matrix, similar to the one-dimensional case. And in the special case of an orthonormal basis, B transpose times B is the identity matrix. So we would get pi u of x is B times B transpose times x. The projected vector pi u of x is still a vector in Rd, but we only require m coordinates, the lambda vector over here, to represent it as a linear combination of the basis vectors of the subspace U. We also effectively got the same result as in the one-dimensional case. Remember, in 1D we got lambda equals B transpose X divided by B transpose B, and we got a projection point pi u of x, which was B transpose X divided by B transpose B times B. Now, B transpose B is now expressed as matrix B transpose times matrix B, but we now have the inverse matrix sitting here instead of dividing by a scalar. That's the only difference between these two results. In this video, we looked at orthogonal projections of a vector onto a subspace of dimension m. We arrived at the solution by exploiting two properties. We must be able to represent the projection using a linear combination of the bases of the subspace, and the difference vector between the original vector and its projection is orthogonal to the subspace. In the next video, we're going to look at a concrete example. In the last video, we derived orthogonal projections of vectors onto m-dimensional subspaces. In this video, we'll run through a simple example. We're going to define x to be a three-dimensional vectors given by 2, 1, 1, which is over here, and we define two basis vectors for our two-dimensional subspace, b1 to be 1, 2, 0, and b2 to be 1, 1, 0. So that means U, which is spanned by b1 and b2, is going to be effectively the plane and its extension. So this all is U. The orthogonal projection was given as pi u of x is B times lambda, and we define B now to be B1 and B2 concatenated, which is 1, 2, 0, 1, 1, 0. And lambda was given as B transpose B inverse times B transpose X. B transpose times X is given as 4, 3 vector. B transpose B is a 2 by 2 matrix, which is 5, 3, 3, 2. Now we solve for lambda as B transpose B inverse times B transpose X, which means we find lambda such that B transpose B lambda equals B transpose X. Using Gaussian elimination, we arrive at lambda equals -1, 3. And this implies our projection of X onto the space spanned by the two B vectors is -1 times B1 plus 3 times B2, which is 2, 1, 0. In our diagram over here, this would correspond to this vector here. This is pi u of x. This result makes sense because our projected point has as a third component the 0, and our subspace requires that a third component is always 0. Our projected vector is still a three-dimensional vector, but we can represent it using two coordinates if we use the basis defined by B1 and B2. Therefore, that is the compact representation of the projection of X onto this lower dimensional subspace. In this video, we looked at a concrete example of the orthogonal projection of a three-dimensional vector onto a two-dimensional subspace. In the next video, we're going to exploit orthogonal projections and derive a dimensionality reduction algorithm called principal component analysis. In this course, we will introduce principal component analysis, or PCA, an algorithm for linear dimensionality reduction. PCA has been around for about 100 years and is still one of the most commonly used techniques for data compression and visualization. High-dimensional data, for example images, often has the property that it lies on a low-dimensional subspace and that many dimensions are highly correlated. Here's an illustration in 2 dimensions. Although the data does not quite lie on a straight line, the data does not vary much in 1 dimension, so that we can express it as if it was on a line with nearly no loss. A key idea behind PCA is to use orthogonal projections to find lower dimensional representations of data that retain as much information as possible, similar to the example that we just looked at. In the following videos, we will derive PCA as an algorithm that minimizes average reconstruction errors by orthogonal projections. In this video, we will introduce the setting of PCA and the high-level idea. Assume we have a data set X in Rd consisting of n vectors. So X is a data set, and we have n vectors x1 to xn, where the xi are d-dimensional vectors. Our objective is to find a low-dimensional representation of the data that is as similar to X as possible. Before we start, let's briefly review 3 important concepts. The first one is that every vector in Rd can be represented as a linear combination of the basis vectors. So let's write this down. So we write xn can be written as the sum of I equals 1 to d of beta in times bi, where in the following we will assume that the bi are an orthonormal basis of Rd. If we assume that we use the dot product as our inner product and b1 to bd are an orthonormal basis, we can also write the beta in as xn transpose times bi, which means we can interpret beta in to be the orthogonal projection of xn onto the one-dimensional subspace spanned by the ith basis vector. The third property is that if we have an orthonormal basis b1 to bm of Rd, and we define B to be the matrix that consists of these orthonormal basis vectors, then the projection of X onto this subspace we can write as X tilde is B times B transpose times X. That means X tilde is the orthogonal projection of X onto the subspace spanned by the M basis vectors. And B transpose times X are the coordinates of X tilde with respect to the basis vectors collected in the matrix B. This is also called the code. So coordinates or code. Now let's have a look at PCA. The key idea in PCA is to find a lower dimensional representation xn tilde of xn that can be expressed using fewer basis vectors, let's say M. We assume the data is centered. That means the dataset has mean 0, and we also assume that B1 to BD are an orthonormal basis of RD. Generally, we can write any xn tilde in the following way. Xn tilde can be written as a sum I equals 1 to M of beta in times bi plus the sum of I equals M plus 1 to D of beta in times bi. So we took this entire thing is still living in RD. So we took our general way of writing any vector in RD, which comes from property 1, and we split the sum in property 1 into two sums. One is living in a m-dimensional subspace, and the other one is living in a d minus m-dimensional subspace, which is an orthogonal complement to this particular subspace. In PCA, we ignore the second term, so we get rid of this part. And then we call the subspace that is spanned by the basis vectors B1 to Bm the principal subspace. So B1 to Bm span the principal subspace. Although xn tilde is still a d-dimensional vector, it lives in an m-dimensional subspace of Rd, and only m coordinates, beta n1 to beta nm, are necessary to represent it. So these ones are the coordinate of this xn tilde vector. The betas are then also called the code or the coordinates of tilde xn with respect to the basis vectors b1 to bm. And the setting now is as follows. Assuming we have data x1 to xn, we want to find parameters beta in and orthonormal basis vectors bi such that the average squared reconstruction error is minimized. And we can write the average squared reconstruction error as follows. We can write j, that's the average squared reconstruction error, is going to be 1 over n times the sum n equals 1 to n. And then we write xn minus xn tilde squared. Let's have a look at an example. We have data living in 2 dimensions, and now we want to find a good one-dimensional subspace such that the squared or average squared reconstruction error of the original data points and their corresponding projections is minimized. Here I'm plotting the original data set with their corresponding projections onto one-dimensional subspaces, and I'm cycling through a couple of options of subspaces, and you can see that some of these projections are significantly more informative than others, and in PCA we are going to find the best one. Our approach is to compute the partial derivatives of j with respect to the parameters. The parameters are the beta in and the bi's. We set the partial derivatives of j with respect to these parameters to 0 and solve for the optimal parameters. But one observation we can already make, and that observation is that the parameters only enter this loss function through xn tilde. This means that in order to get our partial derivatives, we need to apply the chain rule. So we can write dj by d either beta in or bi can be written as dj by dxn tilde times dxn tilde by d either beta in or bi. And the first part we can already compute, and we get dj by dxn tilde is minus 2 over n times xn minus xn tilde transpose. And the other derivatives we compute in the next videos. In the last video we set up the PCA objective, and in this video we will determine our first set of optimal parameters. We make two general assumptions in the beginning. The first thing is that we have centered data. That means that the expected value of our data set is 0. And the second one is that the basis vectors form an orthonormal basis. From the previous video, we carry over the following results. First, we can write our projected data point xn tilde as a linear combination bjn times bj, where bj form the orthonormal basis of our subspace. Our loss function is the average squared reconstruction error between our original data point and the projection. And the partial derivative of our loss function with respect to xn tilde is given by this expression. And now we are ready to compute the partial derivative of j with respect to the beta in parameters as follows. So dj with respect to dbin is the derivative of j with respect to xn tilde times the derivative of xn tilde with respect to beta in. So now we're going to have a closer look at this one here. So dxn tilde by d beta in is simply given by bi for I equals 1 to m. And the reason for this is that if we take the derivative with respect to one fixed beta in, then only the ith component of this sum will play a role. And that's the reason why we end up simply with bi. But that also means that our derivative of j with respect to d beta in is now given as dj by d beta in is minus 2 over n times xn minus xn tilde transpose times bi, where here we used equation C to get the first part, and we plugged in this bi over here. And what we're going to do now is we are going to replace xn tilde using equation A. So we end up with minus 2 over n times xn minus the sum of j equals 1 to m bjn times, so beta jn times bj transpose times bi. And this is given as minus 2 over n times xn transpose times bi minus beta in times bi transpose times bi, where we exploited that the bi form an orthonormal basis. If we multiply bi onto both components here, we end up with the sum of bjn times bj transpose times bi. And since bj transpose times bi is 1 if and only if I equals j and otherwise 0, we end up with only one term, which will be 1. So we end up with minus 2n times xn transpose bi minus beta in. So now we need to set this to 0 in order to find our beta in parameters, and this is 0 if and only if the beta in parameters are given by xn transpose times bi, which we're going to define as equation D. What this means is that the optimal coordinates of xn tilde with respect to our bases are the orthogonal projections of the coordinates of our original data point onto the ith basis vector that spans our principal subspace. In this video, we determined the coordinates of the lower dimensional data as the orthogonal projection of the original data onto the basis vectors that span the principal subspace. In the next videos, we will determine the orthonormal basis that spans that principal subspace. In the last video, we determined the coordinates of the optimal projection with respect to the orthonormal basis that spans our principal subspace. Before we go on and determine the optimal basis vectors, let's rephrase our loss function first. I have copied over the results that we have so far, so the description of our projected data point, our loss function, the partial derivative of our loss function with respect to our projected data point, and the optimal coordinates that we found in the last video. Before we go on and determine the optimal basis vectors, let's rephrase our loss function. This will make it much easier to find our basis vectors. For this, let's have a closer look at the difference vector between our original data point and our projected data point. So you can write, so xn tilde is given by equation A, which is the sum over j equals 1 to m beta jn times bj. If we now use the results for our optimal beta jn parameters from here, we get this is j equals 1 to m xn transpose times bj times bj, where we used d. Now we rewrite this in the following way. This is just a scalar, or dot product in this particular case. Dot products are symmetric, so we can swap the order. And we can also move the scalar over here. So what we end up with is bj times bj transpose times xn. And this one we can write generally as j equals 1 to m times bj transpose xn, where we moved the xn out of the sum. And if we look at this, this is a projection matrix. So this means that xn tilde is the orthogonal projection of xn onto the subspace spanned by the m basis vectors bj, where j equals 1 to m. Similarly, we can write xn as the sum j equals 1 to m of bj times bj transpose times xn plus a term that runs from m plus 1 to d, bj times bj transpose times xn. So we write xn as a projection onto the principal subspace plus a projection onto the orthogonal complement. And this term is the one that is missing over here. And that's the reason why xn tilde is the approximation to xn. So if we now look at the difference vector between xn tilde and xn, what remains is exactly this term. So xn minus xn tilde is the sum j equals m plus 1 to d of bj times bj transpose times xn. So now we can look at this displacement vector, so the difference between xn and its projection, and we can see that the displacement vector lies exclusively in the subspace that we ignore. That means the orthogonal complement to the principal subspace. Let's look at an example in 2 dimensions. We have a data set in 2 dimensions represented by these dots, and now we are interested in projecting them onto the U1 subspace. When we do this and then look at the difference vector between the original data and the projected data, we get these vertical lines. That means they have no x component or no variation in x. That means they only have a component that lives in the subspace U2, which is the orthogonal complement to U1, which is the subspace that we projected onto. So with this illustration, let's quickly rewrite this in a slightly different way. I'm going to write this as sum of j equals m plus 1 to d of bj transpose xn times bj, and we're going to call this now equation E. We looked at the displacement vector between xn and its orthogonal projection onto the principal subspace xn tilde. And now we're going to use this to reformulate our loss function. So from equation B, we get that our loss function is 1 over n times the sum n equals 1 to n of xn minus xn tilde squared. So this is the average squared reconstruction error. And now we're going to use equation E for the displacement vector here. So we rewrite this now using equation E as 1 over n times the sum n equals 1 to capital N. And now we're going to use inside that squared norm this expression here. So we get the sum j equals m plus 1 to d of bj transpose times xn times bj squared. And now we're going to use the fact that the bj's form an orthonormal basis, and this will greatly simplify this expression, and we will get 1 over n times the sum n equals 1 to capital N times the sum j equals m plus 1 to d of bj transpose times xn squared. And now we're going to multiply this out explicitly, and we get 1 over n times the sum over n times the sum over j times bj transpose times xn times xn transpose times bj. So this part is now identical to this part. And now I'm going to rearrange the sums. So I'm going to move the sum over j outside. So I'll have sum over j equals m plus 1 to d times bj transpose, so this is independent of n, times 1 over n, the sum n equals 1 to capital N of xn times xn transpose, and there's a bj from here missing, times bj. So I'm going to bracket it now in this way. And what we can see now is that if we look very carefully, we can identify this expression as the data covariance matrix S, because we assumed we have centered data. So the mean of the data is 0. This means now we can rewrite our loss function using the data covariance matrix, and we get that our loss is the sum over J equals M plus 1 to D of Bj transpose times S times Bj. And we can also use a slightly different interpretation by rearranging a few terms and using the trace operator. So we can now also write this as the trace of the sum of J equals M plus 1 to D of Bj times Bj transpose times S. And we can now also interpret this matrix as a projection matrix. This projection matrix takes our data covariance matrix and projects it onto the orthogonal complement of the principal subspace. That means we can reformulate the loss function as the variance of the data projected onto the subspace that we ignore. Therefore, minimizing this loss is equivalent to minimizing the variance of the data that lies in the subspace that is orthogonal to the principal subspace. In other words, we're interested in retaining as much variance after projection as possible. The reformulation of the average squared reconstruction error in terms of the data covariance gives us an easy way to find the basis vector of the principal subspace, which we'll do in the next video. In the last video, we found that minimizing the average squared reconstruction error is equivalent to minimizing the projection of the variance of the data when projected onto the subspace that we'll ignore in PCA. In this video, we will exploit this insight and determine an orthonormal basis of the m-dimensional principal subspace. Using the results from earlier, over here, we can write our loss function as the sum J equals M plus 1 to D of Bj transpose S times Bj, where S is the data covariance matrix. Minimizing this objective requires us to find the orthonormal basis that spans the subspace that we will ignore. And when we have that basis, we take its orthogonal complement as the basis of the principal subspace. Remember that the orthogonal complement of a subspace U consists of all vectors in the original vector space that are orthogonal to every vector in U. Let us start with an example to determine the B vectors. And let's start in 2 dimensions, where we wish to find a one-dimensional subspace such that the variance of the data when projected onto that subspace is minimized. So we're looking at 2 basis vectors, B1 and B2 in R2. So B1 and B2. And B1 will be spanning the principal subspace, and B2 its orthogonal complement. That means the subspace that we will ignore. We also have the constraint that B1 and B2 are orthonormal, which means that Bi transpose times Bj is delta Ij, meaning that this dot product is 1 if I equals j and 0 otherwise. In our example with our 2 vectors, our loss function is j is B2 transpose times S times B2, with the constraint that B2 transpose times B2 is 1. To solve this optimization problem, we write down the Lagrangian, and the Lagrangian is B2 transpose S B2 plus lambda times 1 minus B2 transpose times B2, where lambda is the Lagrange multiplier. So now we compute the gradients of the Lagrangian with respect to B2 and with respect to lambda and set them to 0. So dl d lambda is 1 minus B2 transpose times B2. And this is 0 if and only if B2 transpose times B2 is 1. So we recover our constraint. So now let's have a look at the partial derivative of L with respect to B2. So we get 2B2 transpose times S from the first term and minus 2 lambda B2 transpose from the second term. And this needs to be 0, and that is 0 if and only if S times B2 is lambda times B2. Here we end up with an eigenvalue problem. B2 is an eigenvector of the data covariance matrix, and the Lagrange multiplier plays the role of the corresponding eigenvalue. If we now go back to our loss function, we can use this expression. We can write J, which was B2 transpose times S times B2. Now we know that S times B2 can be written as lambda times B2. So we get B2 transpose times B2 times lambda, and because we have an orthonormal basis, we end up with lambda as our loss function. Therefore, the average squared reconstruction error is minimized if lambda is the smallest eigenvalue of the data covariance matrix. And that means we need to choose B2 as the corresponding eigenvector, and that one will span the subspace that we will ignore. B1, which spans the principal subspace, is then the eigenvector that belongs to the largest eigenvalue of the data covariance matrix. Keep in mind that the eigenvectors of the covariance matrix are already orthogonal to each other because of the symmetry of the covariance matrix. So if we look at a two-dimensional example, if this is our data, then the best projection that we can get that retains most information is the one that projects onto the subspace that is spanned by the eigenvector of the data covariance matrix, which belongs to the largest eigenvalue. And that is indicated by this long arrow over here. Now let's go to the general case. If we want to find the m-dimensional principal subspace of a d-dimensional data set, and we solve for the basis vectors bj, where j equals m plus 1 to d, we optimize these ones, we end up with the same kind of eigenvalue problems that we had earlier with a simple example. We end up with S times bj equals lambda j times bj for j equals m plus 1 to d. And the loss function is given by the sum of the corresponding eigenvalues. So we can write j is the sum from m plus 1 to d of all lambda j. Also in the general case, the average reconstruction error is minimized if we choose the basis vectors that span the ignored subspace to be the eigenvectors of the data covariance matrix that belong to the smallest eigenvalues. This equivalently means that the principal subspace is spanned by the eigenvectors belonging to the m largest eigenvalues of the data covariance matrix. This nicely aligns with properties of the covariance matrix. The eigenvectors of the covariance matrix are orthogonal to each other because of symmetry, and the eigenvector belonging to the largest eigenvalue points in the direction of the data with the largest variance, and the variance in that direction is given by the corresponding eigenvalue. Similarly, the eigenvector belonging to the second largest eigenvalue points in the direction of the second largest variance of the data, and so on. In this video, we identified the orthonormal basis of the principal subspace as the eigenvectors of the data covariance matrix that are associated with the largest eigenvalues. In the next video, we will put all the pieces together and run through the PCA algorithm in detail. In this video, we'll go through the individual steps of PCA. But before we do this, let me make two comments. When we derived PCA, we made the assumption that our data is centered. That means it has mean 0. This assumption is not necessary to derive PCA, and we would have come to the same result, but subtracting the mean from the data can avoid numerical difficulties. Assume the values of our data are centered around 10 to the 8. Then computing the data covariance matrix requires us to multiply huge numbers, which results in numerical instabilities. An additional second step that is normally recommended after subtracting the mean is to divide every dimension of the centered data by the corresponding standard deviation. This makes the data unit-free and guarantees that the variance of the data in every dimension is 1, but it leaves the correlations intact. Let's have a look at an example. Clearly, this data spreads much more in one dimension than the other dimension, and the best projection of PCA is clear. However, there's a problem with this data set. The two dimensions of the data set are both distances, but one is measured in centimeters and the other one in meters. The one measured in centimeters naturally varies much more than the other one. When we divide each dimension of the data set by the corresponding standard deviation, we get rid of the units and make sure that the variance in each dimension is 1. When we look at the principal subspace of this normalized data set, we can now see that there is actually quite a strong correlation between these two dimensions, and the principal axes have changed. But now let's go through PCA step by step, and we'll have a running example. We're given a two-dimensional data set, and we want to use PCA to project it onto a one-dimensional subspace. The first thing that we do is to subtract the mean. The data is now centered. Next, we divide by the standard deviation. Now the data is unit-free and it has variance 1 along each axis, which is indicated by these two arrows. But keep in mind that the correlations are still intact. Third, we compute the data covariance matrix and its eigenvalues and corresponding eigenvectors. The eigenvectors are scaled by the magnitude of the corresponding eigenvalue in this picture. The longer vector spans the principal subspace, let's call it U. And in the last step, we can project any data point x star onto the principal subspace. To get this right, we need to normalize x star using the mean and standard deviation of the dataset that we use to compute the data covariance matrix. So we're going to have a new x star, and the new x star is going to be the old x star minus the mean of the dataset divided by the standard deviation, and we do this for every dimension in x star. Now we can get the projection of x star as x star tilde, or the projection of x star onto the principal subspace U as B times B transpose times x star, where B is the matrix that contains the eigenvectors that belong to the largest eigenvalues as columns, and B transpose times x star are the coordinates of the projection with respect to the basis of the principal subspace. In this video, we went through the steps of PCA. First, we subtract the mean from the data and send it at 0 to avoid numerical problems. Second, we divide by the standard deviation to make the data unit-free. Third, we compute the eigenvalues and eigenvectors of the data covariance matrix. And finally, we can project any data point onto the principal subspace that is spanned by the eigenvectors that belong to the largest eigenvalues. In the last video, we've gone through the steps of the PCA algorithm. In order to do PCA, we need to compute the data covariance matrix. In d dimensions, the data covariance matrix is a d by d matrix. If d is very high, so in very high dimensions, then computing the eigenvalues and eigenvectors of this matrix can be quite expensive. It scales cubically in the number of rows and columns, in this case, the number of dimensions. In this video, we provide a solution to this problem for the case that we have substantially fewer data points than dimensions. Assume we have a data set given as x1 up to xn in Rd, and we assume that the data is centered, so it has mean 0, then the data covariance matrix is given as S equals 1 over n times x transpose times x, where we define x to be the matrix that consists of x1 transpose up to xn transpose, and that is an n by d matrix. We now assume that n is significantly smaller than d. That means the number of data points is significantly smaller than the dimensionality of the data. And then the rank of the covariance matrix is n. So rank of S equals n. And that also means it has d minus n plus 1 many eigenvalues which are 0. That means that the matrix is not full rank, and the rows and columns are linearly dependent. In other words, there are some redundancies. In the next few minutes, we'll exploit this and turn the d by d covariance matrix S into a full rank n by n covariance matrix without eigenvalues 0. I've just moved the covariance definition up here to have a bit more space on the board. In PCA, we ended up with the following eigenvalue-eigenvector equation. We had S times Bi equals lambda I times Bi, where Bi is a basis vector of the orthogonal complement of the principal subspace. Now let's rewrite this equation a little bit. We're now going to replace S with the definition up here. So we'll get 1 over n times x transpose x, this is S, times Bi equals lambda I times Bi. And now we multiply x from the left-hand side. So we will get x times x transpose x Bi times 1 over n equals lambda I times x times Bi. And now we have a new eigenvector-eigenvalue equation. So lambda I is still an eigenvalue, and now we have eigenvectors x times Bi, which we call Ci, of the matrix 1 over n times x transpose. This means that 1 over n times x transpose has the same non-zero eigenvalues as the data covariance matrix, but this is now an n by n matrix, so that we can compute the eigenvalues and eigenvectors much quicker than for the original data covariance matrix. All right, so this is an n by n matrix, whereas S used to be a d by d matrix. So now we can compute the eigenvectors of this matrix 1 over n times x transpose. And we use this to recover the original eigenvectors, which we still need to do PCA. Currently, we know the eigenvectors of 1 over n times x transpose. And we want to recover the eigenvectors of S. If we left multiply our eigenvalue-eigenvector equation with x transpose, we get the following. So you get 1 over n times x transpose times x transpose times Ci equals lambda I times x transpose times Ci. And now we find our S matrix again. This is S. And this also means that we recover x transpose times Ci as an eigenvector of S that belongs to the eigenvalue lambda I. In this video, we reformulated PCA such that we can efficiently run PCA on data sets where the dimensionality of the data is substantially bigger than the number of data points. We derived PCA from the perspective of minimizing the average squared reconstruction error. However, PCA can also be interpreted from different perspectives. In this video, we'll have a brief look at some of these interpretations. Let's start with a recap what we have done so far. We took a high-dimensional vector x and we projected it onto a lower-dimensional representation z using the matrix B transpose. The columns of this matrix B are the eigenvectors of the data covariance matrix that are associated with the largest eigenvalues. The z values are the coordinates of our data point with respect to the basis vectors which span the principal subspace, and that is also called the code of our data point. Once we have that low-dimensional representation z, we can get a higher dimensional version of it by using the matrix B again, so multiplying B onto z to get a higher dimensional version of the z in the original data space. We found the PCA parameters such that the reconstruction error between x and the reconstruction x tilde is minimized. We can also think of PCA as a linear autoencoder. An autoencoder encodes a data point x and tries to decode it to something similar to the same data point. The mapping from the data to the code is called an encoder. Let's write this down. So this part here is called an encoder. The mapping from the code to the original data space is called the decoder. If the encoder and decoder are linear mappings, then we get the PCA solution when we minimize the squared autoencoding loss. If we replace the linear mapping of PCA with a nonlinear mapping, we get a nonlinear autoencoder. A prominent example of this is a deep autoencoder where the linear functions of the encoder and decoder are replaced with deep neural networks. Another interpretation of PCA is related to information theory. We can think of the code as a smaller compressed version of the original data point. When we reconstruct our original data using the code, we don't get the exact data point back, but a slightly distorted or noisy version of it. This means that our compression is lossy. Intuitively, we want to maximize the correlation between the original data and the lower dimensional code. More formally, this would be related to the mutual information. We would then get the same solution to PCA we discussed earlier in this course by maximizing the mutual information, a core concept in information theory. When we derived PCA using projections, we reformulated the average reconstruction error loss as minimizing the variance of the data that is projected onto the orthogonal complement of the principal subspace. Minimizing that variance is equivalent to maximizing the variance of the data when projected onto the principal subspace. If we think of variance in the data as information contained in the data, this means that PCA can also be interpreted as a method that retains as much information as possible. We can also look at PCA from the perspective of a latent variable model. We assume that an unknown lower dimensional code Z generates data X, and we assume that we have a linear relationship between Z and X. So generally we can then write that X is B times Z plus mu, and maybe some noise. We assume that the noise is isotropic with mean 0 and covariance matrix sigma squared times I. We further assume that the distribution of this Z is a standard normal. So P of Z is Gaussian with mean 0 and covariance matrix, the identity matrix. We can now write down the likelihood of this model. So the likelihood is P of X given Z, and that is a Gaussian distribution in X with mean BZ plus mu and covariance matrix sigma squared I. And we can also compute the marginal likelihood as P of X is the integral of P of X given Z, so that is the likelihood times the distribution on Z dz, and that turns out to be a Gaussian distribution in X with mean mu and with covariance matrix B times B transpose plus sigma squared I. The parameters of this model are mu, b, and sigma squared, and we can write them explicitly down in our model up here. So model parameters are b and mu and sigma squared. We can now determine the parameters of this model using maximum likelihood estimation. And we will find that mu is the mean of the data, and B is a matrix that contains the eigenvectors that correspond to the largest eigenvalues. To get the low-dimensional code of a data point, we can apply Bayes' theorem to invert the linear relationship between z and x. In particular, we are going to get P of z given x as P of x given z. So that is the likelihood, which comes from here, times P of z. So that's our distribution that we have here, divided by the marginal likelihood, P of x, which comes from here. In this video, we looked at 5 different perspectives of PCA that lead to different objectives: minimizing the squared reconstruction error, minimizing the autoencoder loss, maximizing the mutual information, maximizing the variance of the projected data, and maximizing the likelihood in a latent variable model. All these different perspectives give us the same solution to the PCA problem. The strengths and weaknesses of individual perspectives become more clear and important when we consider properties of real data.